What if everything you thought you knew about time and space was only the tip of the iceberg? Picture this. Near the edge of a black hole, time doesn't just slow down, it practically stops. This isn't science fiction. It's the bizarre reality of space-time, the fabric that weaves the universe together. Yet, as mind-bending as that sounds, it's just one small piece of a much larger puzzle. Space-time isn't just a backdrop for the cosmos, it's the stage where the greatest mysteries of existence play out. And today, we're diving into the less traveled corners of this cosmic stage to uncover 30 theories that will challenge everything you thought you knew. From hidden dimensions to alternate realities, these ideas aren't just groundbreaking, they're universe-shaking. So, buckle up. By the end of this journey, you'll see the cosmos in a whole new light. Let's begin. Imagine stepping into a room lined with mirrors where every surface reflects not just your image, but the entire world around you. Now, take that idea and scale it up to the size of the universe. What if everything we perceive as three-dimensional, the stars, planets, and even you, was just a projection like a hologram from a two-dimensional surface? This mind-bending concept is at the heart of the holographic principle, a theory that challenges our understanding of reality itself. The holographic principle suggests that all the information needed to describe our three-dimensional universe could actually be encoded on a two-dimensional boundary, much like how a hologram stores a 3D image on a flat surface. This idea first emerged from the study of black holes, where physicists like Leonard Susskind and Gerard T. Hooft discovered something strange. The amount of information a black hole can hold seems to depend not on its volume but on its surface area. This led to the radical idea that perhaps the universe itself operates in a similar way. As Susskind once put it, the three-dimensional world of ordinary experience may be a kind of illusion, and the ultimate reality could be a vast, flat, two-dimensional information structure. If this is true, it means that the richness of our 3D reality, everything from the texture of a tree's bark to the vastness of a galaxy, could be a kind of cosmic projection, a trick of the light on the grandest scale. But what does this mean for us? If our universe is a hologram, could everything we experience, our thoughts, emotions, and even time itself, be part of this intricate illusion? It's a question that blurs the line between science and philosophy, pushing us to rethink not just the nature of space and time, but the very fabric of existence. And here's where things get even more fascinating. The holographic principle doesn't just challenge our perception of reality, it also hints at a deeper connection between space, time, and information. It suggests that the universe might be fundamentally interconnected in ways we're only beginning to understand. This idea of interconnectedness leads us to the next theory, which explores how space-time itself might be woven together like an intricate tapestry. What if everything you think you know about time is wrong? Picture this. The past, present, and future don't flow in a straight line but exist all at once, like frames in a film reel. This is the heart of the block universe theory, a mind-bending idea that suggests time isn't something that passes, it's a dimension, just like space. In this view, the universe isn't unfolding moment by moment. Instead, every event from the Big Bang to this very second is already fixed in place like a cosmic mosaic. Einstein's theory of relativity plays a huge role here. His equations show that time isn't absolute, it stretches and bends depending on how fast you're moving or how strong gravity is. This leads to some wild implications like the famous twin paradox. Imagine one twin stays on Earth while the other zooms off in a spaceship at near light speed. When the traveling twin returns, they've aged much slower than their Earth-bound sibling. But here's the kicker, from the perspective of the traveling twin, it's the Earth-bound twin who aged slower. This paradox highlights how time is relative, and it supports the idea that past, present, and future are all equally real, just different slices of the same cosmic block. Now here's where it gets even more intriguing. If the block universe theory is true, does free will even exist? If every moment is already set in stone, are we just following a script written by the laws of physics? Or is there still room for choice within this vast, unchanging structure? It's a question that challenges how we see ourselves and our place in the universe. But while the block universe paints time as static, what if space-time is far more dynamic than we realize? What if the very fabric of reality is constantly shifting, bending, and reshaping itself? That brings us to our next theory, where the boundaries of space and time aren't just fixed coordinates, but something far more fluid and alive. In the 1960s, two brilliant minds, John Wheeler and Bryce-DeWitt, set out to tackle one of the greatest puzzles in physics: how to unite quantum mechanics and general relativity. Their groundbreaking work led to the creation of the Wheeler-DeWitt Equation, a mathematical framework that attempts to bridge the gap between these two seemingly incompatible theories. But here's where it gets mind-bending. This equation suggests that time, as we know it, might not be a fundamental feature of the universe. Instead, it emerges as a kind of illusion, a byproduct of deeper quantum processes. Imagine trying to describe the universe without using time as a reference point. It sounds impossible, doesn't it? Yet, that's exactly what the Wheeler-DeWitt equation does. By eliminating time from the equation, it forces us to rethink our understanding of reality. Some physicists argue that this could mean the universe is fundamentally timeless, with past, present, and future existing simultaneously in a static, unchanging structure. Others see it as a sign that our current theories are incomplete, pointing to the need for a new framework that can properly account for time's role. Despite its elegance, the Wheeler-DeWitt equation has sparked intense debate. As physicist Carlo Rovelli once remarked, "It's not that time doesn't exist, it's that it's not what we thought it was." This idea challenges not only our scientific models but also our everyday perception of reality. If time isn't fundamental, what does that mean for causality, for the flow of events, or even for free will? These questions remain at the forefront of modern physics, keeping the Wheeler-DeWitt equation as relevant today as it was when it was first proposed. But what happens when we zoom into the quantum scale? The Wheeler-DeWitt equation hints at a realm where space-time itself might behave in ways that defy our intuition. The next theory we'll explore takes us even deeper into this bizarre quantum landscape, where the very fabric of reality seems to twist and turn in ways that challenge everything we thought we knew. Now let's dive into a fascinating idea that turns our understanding of space-time on its head: the causal set theory. What if space-time isn't the smooth, continuous fabric Einstein described, but instead it's made up of tiny, indivisible building blocks? Imagine the universe as a digital image on a screen. At first glance, it looks seamless, but when you zoom in, you see it's actually made of individual pixels. Causal set theory suggests that space-time might work the same way, composed of discrete, fundamental units that, when seen from a distance, create the illusion of continuity. This theory challenges the very foundation of Einstein's general relativity, which treats space-time as a smooth, flowing entity. But here's the twist: if space-time is fundamentally discrete, it could help bridge the gap between quantum mechanics and gravity, two of the most stubborn puzzles in modern physics. Quantum mechanics deals with the tiny, the discrete, and the probabilistic, while gravity, as described by Einstein, operates in a smooth, continuous framework. Causal set theory offers a way to unify these two worlds by proposing that space-time itself emerges from these discrete building blocks. Mathematically, the theory is rooted in order and causality. It suggests that the fundamental units of space-time are connected in a specific sequence, creating a structure that defines the flow of time and the geometry of space. Think of it like a cosmic domino effect, each event influencing the next, building the universe one step at a time. So here's a thought: could the universe be digital? If space-time is made of these discrete units, it raises profound questions about the nature of reality itself. Are we living in a universe that operates more like a computer program than a continuous, flowing entity? This idea doesn't just challenge our understanding of space-time, it invites us to rethink how the cosmos itself might be structured. As we ponder this, another question arises. If space-time emerges from these deeper, discrete principles, what else might be hidden beneath the surface? Let's explore how space-time might not be fundamental at all, but rather something that emerges from even more basic laws of the universe. Picture the surface of the ocean, where waves rise and fall in a mesmerizing dance. From a distance, the water seems smooth and continuous, a single, unbroken expanse. But zoom in closer, and you'll see that each wave is made up of countless individual droplets, each one part of a deeper, more intricate system. Now imagine space-time as that ocean. What if the fabric of the universe we perceive isn't fundamental at all, but something that emerges from a more basic, hidden layer of reality? This is the core idea behind the Emergent Space-Time theory, a mind-bending concept that challenges everything we thought we knew about the cosmos. According to this theory, space-time isn't the foundation of reality, but rather a byproduct of more fundamental quantum processes. Think of it like a hologram where a three-dimensional image emerges from a two-dimensional surface. In the same way, space-time could be a kind of illusion, an emergent property arising from the complex interactions of quantum bits at the tiniest scales. Physicist Eric Verland, a leading voice in this field, describes it this way: space-time is not something that exists independently. It's something that arises from the entanglement of quantum information. This theory isn't just a standalone idea. It's deeply connected to other groundbreaking concepts like string theory and the holographic principle. String theory suggests that the fundamental building blocks of the universe are tiny, vibrating strings, while the holographic principle posits that all the information in a volume of space can be represented as data on its boundary. Together, these ideas paint a picture of a universe where space-time is a secondary phenomenon, a kind of cosmic mirage that emerges from a deeper, more fundamental reality. So, what does this mean for our understanding of the universe? It invites us to rethink the very nature of reality. Instead of space-time being the stage on which the drama of the cosmos unfolds, it becomes part of the play itself, a dynamic, ever-changing construct shaped by the underlying quantum world. It's a shift in perspective as profound as realizing the Earth isn't the center of the solar system. But here's where it gets even more intriguing. If space-time is emergent, then what's truly fundamental? Some researchers believe the answer lies in information, the idea that the universe is, at its core, a vast network of data. This leads us to the next theory, where information doesn't just describe reality but actively shapes it. What if everything we see, touch, and experience is, in some sense, a kind of cosmic code? Now, let's dive into one of the most baffling mysteries of the cosmos, the information paradox. Black holes, those enigmatic giants of gravity, have long been thought to be the ultimate cosmic shredders. Once something crosses the event horizon, it's gone forever, or so we thought. But here's the twist. According to the laws of quantum mechanics, information can never truly be destroyed. So, what happens to all that information when a black hole devours it? This is the heart of Stephen Hawking's famous paradox. Hawking proposed that black holes emit radiation, now known as Hawking radiation, causing them to slowly evaporate over time. But if a black hole disappears, where does the information about everything it swallowed go? This contradiction between quantum mechanics and general relativity has left physicists scratching their heads for decades. It's a cosmic puzzle that challenges our very understanding of space-time. Enter the holographic principle, one of the leading ideas to resolve this paradox. This theory suggests that all the information swallowed by a black hole isn't lost, it's encoded on its surface like a hologram. In other words, the three-dimensional information of everything that falls in is somehow projected onto the two-dimensional boundary of the black hole. It's a mind-bending concept that redefines how we think about space and information. Another wild proposal is the idea of firewalls. Some physicists argue that just inside the event horizon, there's a fiery wall of energy that destroys anything trying to cross. While this solves the information paradox, it introduces new questions about the nature of black holes and whether they truly have an event horizon as we understand it. As Hawking himself once said, black holes ain't as black as they are painted. So what does all this mean for space-time? If information isn't lost but instead encoded or transformed in some way, it suggests that space-time itself might be a kind of information storage system. This raises an even bigger question. Could the universe itself be a giant hologram with all the information about its contents written on its boundaries? It's a theory that blurs the line between reality and information, opening up a whole new frontier in our understanding of the cosmos. As we ponder the fate of information in black holes, let's explore another fascinating idea: how space-time might encode information in ways we're only beginning to understand. Have you ever wondered if two of the strangest phenomena in physics, wormholes and quantum entanglement, might actually be two sides of the same cosmic coin? This is the mind-bending idea at the heart of the ER EPR Conjecture. Proposed by physicists Leonard Susskind and Juan Maldacena, this theory suggests that entangled particles, those mysterious pairs that seem to communicate instantly across vast distances, might be linked by microscopic wormholes. Yes, wormholes, those hypothetical tunnels through space-time that science fiction loves to dream about. But here's the kicker: these aren't the kind you could fly a spaceship through. Instead, they're unimaginably tiny, a bridge between the fabric of space-time and the quantum realm. Susskind once described this idea as a radical new way of thinking about space, time, and quantum entanglement. Think of it like this: imagine the universe as a giant tapestry, with each thread representing a connection between particles. These threads aren't just symbolic. They could be actual, physical links, wormholes stitching the cosmos together at the most fundamental level. Juan Maldacena added to this, saying, "Entanglement might be the glue that holds space-time together." It's a breathtaking vision, one that could help us finally bridge the gap between quantum mechanics and Einstein's theory of gravity, two frameworks that have stubbornly refused to play nice for over a century. But what does this mean for our understanding of reality? If entangled particles are connected by wormholes, it could imply that space-time itself is woven from quantum entanglement. Picture the universe not as a smooth, continuous fabric, but as a dynamic network of interconnected threads, constantly shifting and evolving. This idea doesn't just challenge our intuition, it rewrites the rules of how we think about space and time. So, the next time you hear about quantum entanglement, consider this: those particles might not just be spooky in the way Einstein described. They might be holding the very fabric of our universe together. And if that doesn't make you pause, just wait, because entanglement doesn't stop at connecting particles. It might also play a starring role in the very structure of space-time itself. But more on that in a moment. Now, let's take a journey down to the smallest scales of the universe, where the fabric of space-time might not be smooth and serene, but instead a seething, frothy chaos. This is the realm of quantum foam theory, a mind-bending idea that suggests space-time itself could be bubbling and fluctuating at the tiniest levels, like a fizzy drink filled with countless microscopic bubbles. Imagine looking at the surface of a calm lake. It seems perfectly smooth from a distance, but up close you'd see ripples, waves, and tiny disturbances. Quantum foam proposes that space-time operates in a similar way, but on a scale so small it's almost impossible to comprehend. This theory arises from the strange and counterintuitive world of quantum mechanics, where particles pop in and out of existence and uncertainty reigns supreme. At these incredibly tiny scales, the very fabric of reality might be turbulent, with space-time constantly twisting, warping, and bubbling. It's as if the universe itself is alive with energy, never truly at rest. But what does this mean for the nature of reality? If space-time is frothy and chaotic at its core, could it mean that our perception of a stable, orderly universe is just an illusion? Testing this theory is no small feat. The scales involved are so minuscule that they're far beyond our current technological capabilities to observe directly. However, some scientists believe that studying phenomena like black holes or the remnants of the Big Bang might offer clues. For instance, if space-time is inherently unstable, it could leave subtle imprints on the light from distant stars or the gravitational waves rippling through the cosmos. These tiny signatures might one day reveal the chaotic underpinnings of reality itself. But here's a question to ponder. If space-time is frothy and unstable at the quantum level, how does it hold together on the larger scales we experience every day? Could this chaotic foundation somehow give rise to the smooth, predictable universe we see around us? It's a mystery that challenges our understanding of space, time, and the very essence of existence. And speaking of energy shaping space-time, that brings us to our next theory, one that explores how the very forces of the universe might bend and mold the fabric of reality itself. Let's zoom in on one of the strangest phenomena in quantum physics, the Casimir Effect. Picture two uncharged metal plates placed incredibly close to each other in a vacuum, a space completely devoid of matter. You'd expect nothing to happen, right? But here's where things get wild. The plates are pushed together by an invisible force, as if space itself is exerting pressure. This is the Casimir Effect in action, and it reveals something profound about the nature of space-time. So, what's really going on? According to quantum mechanics, even a perfect vacuum isn't truly empty. Instead, it's teeming with quantum fluctuations, tiny, fleeting bursts of energy that pop in and out of existence. These fluctuations create a kind of quantum foam, filling every corner of space-time. When the plates are brought close together, they limit the types of fluctuations that can exist between them, creating a pressure difference that pushes them together. It's like space itself is alive, constantly bubbling with energy. This bizarre phenomenon has huge implications for our understanding of the universe. Physicists like Hendrik Casimir, who first predicted this effect in the late 1940s, realized that it challenges our classical view of empty space. Instead of being a void, space is a dynamic, energy-filled arena. Nobel laureate Frank Wilczek once described it as a seething, writhing froth of virtual particles, a poetic way to capture the chaos of the quantum realm. But the Casimir Effect isn't just a theoretical curiosity. It might hold clues to one of the biggest mysteries in cosmology: dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, and some scientists believe it could be linked to the energy of the vacuum itself. If empty space is brimming with quantum fluctuations, could these tiny bursts of energy somehow contribute to the vast, unseen force shaping the cosmos? It's a tantalizing idea that bridges the microscopic and the cosmic. Now, think about this. What if the vacuum of space isn't just a backdrop for the universe, but an active participant in its evolution? The Casimir Effect hints at a universe where nothingness is anything but empty. It's a reminder that even in the void, there's energy, movement, and potential. And as we explore the role of energy in shaping space-time, we'll see how these quantum whispers might hold the key to understanding the very fabric of reality. What if everything we perceive, our entire universe, is just a three-dimensional membrane floating in a vast, higher-dimensional space? This is the core idea behind the brain world scenario, a mind-bending theory that emerges from the depths of string theory. Imagine our universe as a thin sheet, a brain, existing within a much larger, multidimensional bulk. According to this idea, the forces and particles we know are confined to our brain, while gravity, unique among the fundamental forces, can leak into the extra dimensions. This could explain why gravity feels so weak compared to electromagnetism or the strong nuclear force. As physicist Lisa Randall puts it, gravity's apparent feebleness might just be a sign that it's spreading out into dimensions we can't see. This theory doesn't just challenge our understanding of space-time, it opens up a universe of possibilities. If higher dimensions exist, they could be hiding in plain sight, curled up so tightly that even our most advanced instruments can't detect them. Picture this: every point in our three-dimensional world might actually be a doorway to a hidden dimension, like a tiny, invisible fold in the fabric of reality. Could it be that we're surrounded by dimensions we've never even noticed? It's a question that blurs the line between science and science fiction. As we ponder this idea, it's worth considering how space-time itself might be warped by these extra dimensions. What if the way we experience gravity or even time is just a shadow of a much richer, multidimensional reality? This leads us to the next frontier of thought, the way space-time might twist, stretch, and fold in ways we're only beginning to understand. What if we could travel to distant stars without breaking the ultimate speed limit of the universe? The dream of faster-than-light travel has fascinated scientists and dreamers alike for decades, and in 1994, physicist Miguel Alcubierre proposed a theoretical solution that might just make it possible. His idea, the Alcubierre warp drive, a concept that doesn't involve moving through space faster than light, but instead manipulates space-time itself. Picture this: instead of a spaceship zooming through the cosmos, the ship sits inside a bubble of warped space-time. The space in front of the ship contracts while the space behind it expands, effectively allowing the ship to ride this wave of distorted space-time without ever exceeding the speed of light. It's like surfing on the fabric of the universe itself. Alcubierre's warp drive is rooted in Einstein's theory of general relativity, which allows for the bending and stretching of space-time. The beauty of this idea is that it sidesteps the problem of relativity, which states that nothing with mass can reach or exceed the speed of light. Instead, the warp drive cleverly exploits a loophole. The ship itself doesn't move faster than light. It's the space around it that does the work. But here's the catch: this concept relies on something called exotic matter, a hypothetical substance with negative energy density. Exotic matter would be required to create the warping effect, and as of now, we have no evidence that such matter exists. As Alcubierre himself once said, the warp drive is a fascinating idea, but it's not something we can build tomorrow. It's a glimpse into what might be possible if we push the boundaries of our understanding. The challenges don't end there. Even if exotic matter exists, the amount needed to power a warp drive would be staggering. Some estimates suggest it would require the energy equivalent of the mass of Jupiter just to move a small ship. And then there's the question of controlling the warp bubble. Without precise control, the ship could end up in a completely unintended destination or, worse, tear itself apart. Despite these hurdles, the Alcubierre warp drive remains a tantalizing possibility, a beacon of hope for those who dream of exploring the stars. Imagine a future where humanity could visit distant galaxies, not in generations, but in a matter of weeks or months. It's a vision that keeps scientists and dreamers alike looking to the stars. And speaking of exotic matter, this mysterious substance isn't just a key to warp drives. It might also hold the answers to other mind-bending space-time theories. Let's explore how exotic matter could unlock even more secrets of the universe. What if the key to bending the fabric of space-time lies in a type of matter so strange it defies everything we know about physics? Enter exotic matter, a theoretical substance with negative energy density. Unlike ordinary matter, which gravitationally attracts, exotic matter would repel, creating a kind of anti-gravity effect. This bizarre property makes it a prime candidate for two of the most mind-bending concepts in science: stabilizing wormholes and powering warp drives. Imagine a wormhole, a shortcut through space-time connecting two distant points. While Einstein's equations allow for their existence, they're inherently unstable. Pass through one and it would collapse faster than you could say interstellar travel. But here's where exotic matter comes in. Some physicists suggest that its repulsive force could counteract the wormhole's natural tendency to collapse, effectively holding it open long enough for travel. Similarly, warp drives, like the famous Alcubierre drive, rely on exotic matter to compress space-time in front of a spacecraft while expanding it behind, enabling faster-than-light travel without breaking the laws of physics. The catch: exotic matter has never been observed in nature, and creating it in a lab is a monumental challenge. According to physicist Kip Thorne, exotic matter with negative energy density is not something we can just cook up in a kitchen. It requires conditions that push the boundaries of our current understanding of quantum mechanics. Even if we could produce it, the amounts needed for something like a warp drive are staggering, bordering on the impossible, at least for now. So, could exotic matter be the key to unlocking the secrets of space-time manipulation? It's a tantalizing possibility, but one that remains firmly in the realm of theory. Yet the very idea pushes us to question what's possible and challenges us to rethink the limits of the universe. And as we ponder this, another question arises. If we could manipulate space-time in such profound ways, what other mysteries might we uncover? What if time itself could take on a physical form, like a crystal? This isn't science fiction, it's the mind-bending idea behind time crystals, a new phase of matter that defies everything we thought we knew about time and space. Unlike traditional crystals, which have repeating patterns in space, time crystals repeat their structure over time. They oscillate or tick without any external energy input, creating a loop that seems to dance to the rhythm of time itself. Nobel laureate Frank Wilczek, who first proposed this idea, described it as a way to see time as something more tangible, almost like a material that can be shaped and studied. Time crystals don't just exist in theory, they've been created in labs using quantum systems. These strange structures challenge our understanding of space-time by showing that time, much like space, can have its own patterns and symmetries. Imagine a world where time isn't just a linear flow but something that can crystallize, forming loops or cycles that repeat endlessly. This discovery could revolutionize quantum computing, where time crystals might be used to create ultra-stable qubits, the building blocks of quantum systems. Their ability to maintain coherence over time, even in chaotic environments, could be the key to unlocking the full potential of quantum technology. But what does this mean for our understanding of the universe? Time crystals push us to rethink the very fabric of reality. If time can crystallize, what other hidden symmetries might exist in space-time? This idea ties into one of the most fundamental concepts in physics, symmetry. From the tiniest particles to the vast expanse of the cosmos, symmetry often holds the key to unlocking the universe's deepest secrets. And as we'll see next, symmetry plays a starring role in another groundbreaking theory that could reshape our understanding of existence itself. Have you ever wondered if the universe could be a mirror image of itself? This isn't just a philosophical musing, it's a question that lies at the heart of one of the most intriguing symmetries in physics, CPT symmetry. CPT stands for charge, parity, and time, and it's a fundamental principle that suggests the laws of physics remain unchanged if you flip the charge of particles, reverse their spatial coordinates like a mirror reflection, and run time backward. At first glance, it might sound like science fiction, but this symmetry is deeply rooted in the fabric of space-time itself. Imagine flipping the universe like a coin, turning every particle into its antiparticle, reflecting the entire cosmos as if in a mirror and reversing the flow of time. According to CPT symmetry, the universe should still behave the same way under these transformations. It's a stunning idea, one that hints at a profound balance in the laws governing reality. But what does this mean for the structure of space-time? Physicists believe that CPT symmetry plays a crucial role in shaping the universe, influencing everything from the arrow of time to the very origins of the Big Bang. Take the arrow of time, for example. We experience time as flowing in one direction forward, but CPT symmetry suggests that, on a fundamental level, the universe doesn't actually care which way time flows. This raises fascinating questions. Could the Big Bang have been a moment where time itself flipped direction? Some theories propose that the early universe might have been a perfectly symmetrical event, with time flowing in two directions simultaneously. As physicist John Wheeler once said, "We live on an island of knowledge surrounded by a sea of ignorance." CPT symmetry pushes us to explore that sea, challenging our understanding of time and causality. But here's where it gets even more mind-bending. If the universe obeys CPT symmetry, could it be a reflection of itself? Could there be a parallel cosmos where particles are antiparticles, left is right, and time flows backward? This idea isn't just speculative, it's a stepping stone to the multiverse theory, which suggests that our universe might be just one of countless others, each with its own unique set of physical laws. And if CPT symmetry holds true, these universes might not be as different as we think. They could be mirror images connected by the same underlying principles that govern space-time. So, as we ponder these questions, let's take a moment to reflect. Could the universe we see be just one side of a cosmic coin, with an invisible reflection waiting to be discovered? And if so, what does that mean for our understanding of reality? The answers might lie in the next theory, where we'll explore how space-time could bridge the gap between universes, revealing a multiverse that's both vast and intimately connected. What if everything we know about the universe is just a tiny fraction of a much larger reality? Imagine a cosmos so vast and complex that our universe is merely one thread in an infinite tapestry. This is the concept of the multiverse, a mind-bending idea suggesting that our universe might be just one of countless others, each with its own unique set of physical laws and space-time structures. Think about it. In one universe, space-time might stretch and curve in ways we can barely comprehend, while in another, time itself could flow backward or exist in loops. The laws of physics we take for granted, like gravity or the speed of light, could be completely different elsewhere. As physicist Brian Greene once put it, the multiverse is not just one idea, but a spectrum of possibilities, each painting a different picture of reality. The implications are staggering. If the multiverse exists, it challenges our understanding of what reality truly is. Are the constants of nature, like the strength of gravity or the charge of an electron, merely random outcomes in an endless sea of possibilities? Or is there some deeper order governing the multiverse that we have yet to uncover? Now consider this. If space-time can take on infinite forms across different universes, what does that mean for singularities, those mysterious points where the fabric of space-time seems to break down? Could they be gateways to other universes, or perhaps the seeds from which new realities are born? The answers might lie in the next theory, where we'll explore the enigmatic role of singularities in shaping the cosmos. For now, let your mind wander through the infinite possibilities of the multiverse. What kind of universe would you want to explore? One where time stands still, or one where space itself is alive with motion? The multiverse invites us to dream bigger than ever before, reminding us that the cosmos is far stranger and more wondrous than we can imagine. What if the most extreme objects in the universe, black holes, aren't quite as hidden as we think? For decades, the event horizon has been seen as an impenetrable veil, shielding the singularity at the center of a black hole from the outside universe. But what if that veil could be torn away? Enter the naked singularity conjecture, a mind-bending idea that suggests singularities might exist without the protective cloak of an event horizon. Roger Penrose, one of the greatest minds in theoretical physics, once said, the idea of a naked singularity challenges the very foundation of our understanding of space-time. And he's right. If singularities could exist naked, exposed to the universe, they would defy everything we thought we knew about gravity, causality, and the laws of physics. Unlike the singularities hidden behind black holes, which are safely tucked away from observation, naked singularities could potentially be observed directly. Imagine a point in space where gravity becomes infinite, time ceases to function, and the fabric of reality itself unravels, all visible to the outside universe. The implications are staggering. A naked singularity could act as a cosmic window into the deepest mysteries of space-time, revealing secrets about quantum gravity and the unification of physics. But it also raises questions. Would the laws of nature break down entirely in such a scenario, or would new, as yet undiscovered laws come into play? Some physicists even speculate that naked singularities could serve as bridges to other universes or dimensions, offering a glimpse into realities beyond our own. This brings us to a tantalizing question. Could naked singularities be the key to unlocking the true nature of space-time? If we could observe one, it might revolutionize our understanding of the universe. But here's the twist. What if space-time itself is shaped not just by gravity, but by quantum effects we're only beginning to comprehend? That's where the next theory takes us, diving into the quantum realm and its profound influence on the fabric of reality. What if everything we think we know about space and time is just the tip of the iceberg? Enter the quest for quantum gravity, a theory that seeks to unite the two most powerful yet seemingly incompatible frameworks in physics, quantum mechanics and gravity. Quantum mechanics governs the bizarre world of the very small, where particles can exist in multiple states at once. Gravity, on the other hand, is the force that shapes the cosmos, bending space-time on the grandest scales. But what happens when you try to bring these two together? That's where the real mystery begins. At the heart of this mystery is the idea that space-time itself might not be smooth and continuous, as Einstein's theory of general relativity suggests. Instead, it could be made up of tiny, indivisible units. Think of it like pixels on a screen, but for the fabric of reality. Leading this charge are two major contenders: loop quantum gravity and string theory. Loop quantum gravity proposes that space-time is woven together by loops of energy, creating a kind of quantum fabric. String theory, on the other hand, imagines the universe as a symphony of vibrating strings, where every particle and force is a different note in the cosmic melody. As physicist Carlo Rovelli once said, space and time are not things, they are relations between things. This perspective challenges us to rethink reality itself. Imagine a universe where space-time isn't a smooth stage but more like a mosaic, where every tiny piece plays a role in the grand design. What would that mean for black holes, the Big Bang, or even our everyday experience of time? But the story doesn't end there. As we dig deeper into the quantum realm, we begin to see hints that entropy, the measure of disorder in a system, might hold the key to understanding space-time itself. Could it be that the flow of time is somehow tied to the increase of entropy? That's a question that ties this theory to the next, where we'll explore the enigmatic relationship between space-time and the arrow of time. For now, though, let's sit with the idea that the universe might be far stranger and far more beautiful than we ever imagined. Black holes are often thought of as cosmic vacuum cleaners, swallowing everything in their path, including light itself. But what if I told you that these seemingly destructive objects also carry a mysterious property called entropy? This discovery, first proposed by physicist Jacob Bekenstein in the 1970s, upended our understanding of black holes and space-time itself. Bekenstein showed that black holes aren't just empty voids, they have entropy, a measure of disorder or information. This was shocking because entropy is usually associated with matter, not the absence of it. Stephen Hawking later built on this idea, revealing that black holes emit radiation now famously known as Hawking radiation, and that they slowly evaporate over time. But here's the paradox: if a black hole evaporates, what happens to all the information it swallowed? Does it just vanish, breaking the fundamental laws of physics that say information can't be destroyed? This question has sparked decades of debate, with Hawking himself famously saying, "Not only does God play dice, but he sometimes throws them where they cannot be seen." The implications are profound. If black holes have entropy, it suggests that space-time itself might be far more complex than we thought. Could entropy be the key to understanding the fabric of the universe? Some physicists argue that entropy might not just be a property of space-time, it could be the foundation of it. This idea ties into the concept of emergent space-time, where the universe's structure isn't fundamental but arises from deeper, more fundamental processes. So, what does this mean for our understanding of reality? If space-time is emergent, then what we perceive as the universe might just be the surface of something far more intricate. It's a thought that challenges everything we think we know, leaving us to wonder, is the universe itself a kind of cosmic hologram? Let's explore that idea next. What if the universe we observe is just a projection of something far more complex? This is the mind-bending idea at the heart of the AD/CFT correspondence, a theory that suggests a higher dimensional space could be mathematically equivalent to a lower dimensional theory. It's like taking a three-dimensional hologram and realizing it can be perfectly described by a two-dimensional surface. This duality, first proposed by physicist Juan Maldacena, bridges the gap between gravity and quantum field theory, two frameworks that have long resisted unification. As Maldacena himself put it, the AD/CFT correspondence shows that gravity in a higher dimensional space can be equivalent to a quantum field theory without gravity in one fewer dimension. But what does this mean for our understanding of space-time? Imagine a universe where dimensions aren't fixed but interchangeable, where the fabric of reality might be encoded on its boundaries. This is the essence of the holographic principle, which suggests that all the information in a volume of space can be represented as data on its surface. It's as if the universe is a cosmic hologram, with every event and particle in the bulk of space-time being a projection of information stored on its edges. The implications are staggering. If true, this could revolutionize how we think about the nature of reality, offering a new way to reconcile quantum mechanics and general relativity. It also hints at a profound connection between geometry and physics, where the shape of space-time itself might hold the key to understanding the fundamental laws of the universe. And speaking of geometry, this leads us to the next theory, where the very structure of space-time takes center stage. Picture this: the fabric of the universe, the very stage on which everything unfolds, might not be as featureless as it seems. What if space-time itself has a shape, not just a flat, endless expanse, but something far more dynamic, curved, twisted, or even folded in ways that defy our everyday intuition? This isn't science fiction, it's a cornerstone of modern cosmology. The geometry of space-time isn't just an abstract curiosity. It shapes how the universe evolves, from the smallest particles to the largest galaxies. At the heart of this idea is the question: is space-time flat, curved, or something even stranger? If it's flat, the universe could expand forever, gradually cooling into an eternal quiet. But if it's curved, the story changes dramatically. A positively curved universe might eventually collapse back in on itself in a big crunch, while a negatively curved one could stretch into an endless, accelerating expansion. The shape of space-time isn't just a detail. It's a cosmic blueprint that determines the ultimate fate of everything we know. But how do we even begin to measure something as vast and intangible as the geometry of the universe? Here's where dark energy and the cosmic microwave background come into play. Dark energy, that mysterious force driving the universe's accelerated expansion, leaves its fingerprints on the large-scale structure of space-time. Meanwhile, the cosmic microwave background, the faint afterglow of the Big Bang, acts like a cosmic map, revealing subtle patterns that hint at the universe's underlying shape. As cosmologist George Smoot once said, looking at the cosmic microwave background is like looking at the DNA of the universe. These clues help us piece together the puzzle of space-time's geometry. And then there's the bigger question: could the shape of space-time not only describe the universe but also determine its destiny? Imagine a universe where space-time's curvature dictates whether galaxies drift apart forever or eventually collide. It's a profound thought, one that challenges us to rethink our place in the cosmos. But what if space-time's structure isn't just shaped by gravity and dark energy? What if quantum fields, those invisible forces governing the smallest scales, also play a role? This is where the boundaries of our understanding blur, inviting us to explore even deeper mysteries. Imagine the universe as a vast, shimmering ocean, not of water, but of invisible energy fields stretching across space and time. This is the essence of quantum field theory, a framework that suggests every particle and force in existence is just a ripple, a vibration in these fields. These fields aren't just empty space, they're alive, constantly fluctuating, and giving birth to particles that make up everything we see, from the stars in the sky to the ground beneath our feet. Think of it like this: if space-time were a cosmic symphony, quantum fields would be the instruments, each playing their part to create the music of the universe. Electrons, quarks, even photons, they're all notes arising from these fields. And just as a violin string vibrates to produce sound, particles emerge as excitations in their corresponding fields. This idea isn't just theoretical. It's been confirmed by countless experiments, from the discovery of the Higgs boson to the behavior of particles in accelerators. One of the most profound implications of quantum field theory is how it reshapes our understanding of reality. It suggests that what we perceive as solid matter is, at its core, just energy manifesting in different forms. As physicist Richard Feynman once said, "The world is a dynamic mess of jiggling things. This mess is the quantum field, a fundamental layer of existence that underlies everything we know." But here's where it gets even more fascinating. These fields aren't static, they're influenced by something called symmetry breaking. Imagine a perfectly balanced spinning top. It looks the same from every angle. But as it slows down and falls, it breaks that symmetry, choosing one direction over the others. In the same way, the early universe was a place of perfect symmetry, but as it expanded and cooled, quantum fields underwent symmetry breaking, giving rise to the forces and particles we recognize today. This process not only shaped the cosmos, but also set the stage for the complexity we see around us. So, what does this mean for space-time? It suggests that the very fabric of reality is woven from these fields, and every event, every interaction, is a dance of energy within this cosmic tapestry. The next time you look up at the night sky, remember, you're not just seeing stars and galaxies, you're witnessing the vibrations of quantum fields, the heartbeat of the universe itself. And as we explore this idea further, we'll see how symmetry breaking plays an even deeper role in shaping space-time, leading us to theories that challenge our understanding of existence itself. But that's a story for the next chapter in this cosmic journey. Now, let's step into a moment that changed everything, the symmetry-breaking events of the early universe. Picture this, a cosmos so perfectly balanced that every force and particle existed in harmony, like a flawless dance. But then, something shifted. The universe cooled and symmetry broke, like a mirror shattering into countless fragments. This wasn't chaos, it was the birth of structure, the moment space-time itself began to take shape. These events didn't just alter the universe, they rewrote the rules. Forces like electromagnetism and the weak nuclear force split apart, particles gained mass, and the Higgs field emerged as a cosmic sculptor, giving form to the building blocks of matter. As physicist Brian Greene once put it, Symmetry breaking is the universe's way of transitioning from simplicity to complexity. But here's the question: could this very process explain why the universe is so intricate today? Could the breaking of symmetry be the key to understanding everything from galaxies to gravity? As we marvel at the elegance of these events, it's worth considering how they connect to the mysteries we still face. For instance, could dark matter, the invisible glue holding galaxies together, be another echo of symmetry breaking? Could it be influencing the very fabric of space-time in ways we're only beginning to grasp? The answers might lie in the shadows of the cosmos, waiting to be uncovered. What if I told you that the vast majority of the universe is made up of something we can't see, touch, or even detect directly? This invisible force, known as dark matter, is one of the greatest mysteries in modern astrophysics. While it doesn't emit light or interact with electromagnetic forces, its presence is undeniable thanks to its gravitational effects. Dark matter's gravitational pull acts like an invisible hand, shaping the very fabric of space-time and influencing the evolution of our cosmos on a grand scale. To understand how dark matter interacts with space-time, picture this. Imagine a trampoline representing the fabric of space-time. Now place a heavy bowling ball in the center. That's a massive object like a galaxy. But here's the twist: the bowling ball isn't alone. Surrounding it are countless smaller, invisible weights, dark matter particles, that press into the trampoline, creating a deeper, more complex curvature. This extra tug from dark matter doesn't just affect the shape of space-time. It also dictates how galaxies form, how they cluster together, and even how they move through the universe. Astrophysicist Vera Rubin once said, "It's the discrepancy between what we see and what we know must be there that keeps us searching." Her work on galaxy rotation curves revealed that the outer regions of galaxies spin faster than they should if only visible matter were present. This discovery was a groundbreaking clue that dark matter exists and plays a crucial role in shaping the cosmos. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. But dark matter's influence on space-time goes even further. It's not just about holding galaxies together, it also affects the large-scale structure of the universe. Think of dark matter as the scaffolding upon which galaxies and galaxy clusters are built. Over billions of years, its gravitational pull has drawn matter into vast cosmic webs, creating the intricate patterns we observe in the universe today. And as the universe expands, dark matter continues to shape how space-time stretches and evolves. Now, here's where things get even more intriguing. While dark matter tugs at space-time, there's another mysterious force at work: dark energy. This enigmatic energy seems to be doing the opposite, pushing space-time apart and accelerating the expansion of the universe. Could these two forces, dark matter and dark energy, be working in tandem to shape the fate of the cosmos? That's a question scientists are still trying to answer as they unravel the secrets of space-time. In the late 1990s, astronomers made a discovery that shook our understanding of the universe. The expansion of the cosmos isn't slowing down, it's speeding up. This revelation led to the concept of dark energy, a mysterious force that seems to permeate the fabric of space-time itself, pushing galaxies apart at an ever-increasing rate. But what exactly is dark energy, and how does it connect to the very structure of space-time? Dark energy is thought to make up about 68% of the universe, yet it remains one of the greatest mysteries in modern cosmology. Some scientists believe it could be linked to something called the cosmological constant, a term Einstein introduced into his equations of general relativity to describe a static universe. Ironically, Einstein later called this his greatest blunder when the universe was found to be expanding. But now, the cosmological constant is back in the spotlight as a possible explanation for dark energy. Cosmologist Sean Carroll once noted, "Dark energy might be the simplest explanation for the accelerating universe, but it's also the most perplexing." So what does this mean for space-time? If dark energy continues to dominate, the universe could expand indefinitely, stretching space-time to such an extreme that galaxies drift out of each other's reach, leaving the cosmos cold, dark, and empty, a scenario cosmologists call the Big Freeze. But could dark energy also hold clues to the ultimate fate of space-time itself? Some theories suggest it might even tear apart the very fabric of space-time in a distant future, leading to what's known as the Big Rip. This brings us to an intriguing question. Could the behavior of dark energy be influenced by something even more fundamental, like quantum entanglement? As we'll explore next, the strange connections between particles on the quantum level might have profound implications for how space-time operates on the largest scales. After all, the universe is full of surprises, and dark energy is just one piece of a much larger cosmic puzzle. What if the very fabric of space-time is held together by invisible threads of quantum entanglement? This mind-bending idea takes us into the realm of quantum mechanics, where particles can become mysteriously linked, no matter how far apart they are. This phenomenon, called entanglement, is one of the strangest and most fascinating aspects of the quantum world. Imagine two particles separated by billions of light years, yet if you measure one, the other instantly reacts as if they're still connected. Albert Einstein famously called this spooky action at a distance, but today, physicists are exploring whether this spookiness might be the glue that binds space-time itself. One of the most intriguing theories bridging quantum entanglement and space-time is ER equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena. This idea suggests that entangled particles might be connected through tiny, invisible tunnels in space-time known as wormholes. In other words, entanglement could be a kind of cosmic stitching, weaving together the structure of the universe. As Susskind once said, the geometry of space-time and the quantum entanglement of particles are two sides of the same coin. This theory doesn't just connect particles, it could also offer clues about quantum gravity, the long-sought-after framework that unites quantum mechanics and Einstein's theory of general relativity. But what does this mean for the universe as a whole? If entanglement truly underpins space-time, then the cosmos might be far more interconnected than we ever imagined. Picture a vast cosmic web with every particle, star, and galaxy linked through an intricate network of quantum threads. It's a universe where distance and separation might be illusions, and the boundaries of space-time are far more fluid than we once thought. As we ponder this extraordinary possibility, it's worth asking, could entanglement also play a role in the mysterious nature of time itself? Some theories suggest that time loops, those hypothetical curves where the past and future intersect, might be tied to the quantum connections between particles. If entanglement is the foundation of space-time, could it also hold the key to understanding time travel or the arrow of time? The answers might be closer than we think, hidden in the strange, spooky dance of entangled particles. Now, let's take this idea even further and explore how time loops could reshape our understanding of space-time. What if you could travel back in time and meet your younger self, not through science fiction, but as a real possibility within the fabric of the universe? This is the tantalizing idea behind closed time-like curves, or CTC, a concept that bends the very rules of space-time. These are theoretical loops where time folds back on itself, creating a path that could, in theory, allow you to revisit moments in the past. But how does this work, and what does it mean for our understanding of reality? At the heart of closed time-like curves is Einstein's theory of general relativity, which describes how massive objects warp space-time. Under extreme conditions like near a black hole or in the presence of exotic matter with negative energy density, space-time could curve so dramatically that it forms a loop. Imagine a treadmill where time repeats itself, allowing events to cycle endlessly. This isn't just a wild idea, it's a mathematically valid solution to Einstein's equations. Renowned physicist Kip Thorne once said, "Closed time-like curves are the ultimate cosmic paradox, a way for the universe to challenge our understanding of cause and effect." But here's the catch: these loops would turn causality on its head. If you could travel back in time, could you prevent your own birth, or create a paradox where your actions erase the very events that led to your existence? These questions aren't just philosophical, they're scientific challenges that force us to rethink the foundations of physics. Some theories suggest that quantum mechanics might step in to prevent such paradoxes, acting as a cosmic referee to keep the timeline consistent. Others propose that multiple timelines could branch off, creating parallel universes where every possible outcome exists. What's especially fascinating is the role of exotic matter in making closed time-like curves possible. This hypothetical material, with its negative energy density, could stabilize the curves and prevent them from collapsing. But here's the kicker: exotic matter has never been observed, and its existence remains purely theoretical. Without it, CTCs might remain locked in the realm of imagination. So, could time travel ever become a reality within these loops? The answer lies at the intersection of general relativity and quantum mechanics, two of the most profound yet incompatible theories in physics. As we continue to explore the mysteries of space-time, one thing is clear: the universe is far stranger and more interconnected than we ever imagined. And speaking of connections, what happens when we introduce quantum fluctuations into the mix? How might these tiny, random ripples in space-time influence the fabric of reality? Let's dive into that next. Imagine the universe as a vast, quiet ocean, seemingly calm on the surface. But beneath that stillness lies a turbulent world of constant activity, tiny ripples and waves that never stop. This is the essence of quantum fluctuations, the mysterious and unpredictable movements of energy that occur even in the emptiest regions of space. These fluctuations are not just random noise, they might hold the key to understanding how the universe itself was born. According to modern cosmology, quantum fluctuations in the early universe were like seeds scattered across the fabric of space-time. As the universe expanded rapidly during a period called inflation, these tiny ripples were stretched and amplified, eventually becoming the building blocks of everything we see today: galaxies, stars, and even the cosmic web that connects them. Renowned cosmologist Stephen Hawking once described this process as the universe writing its own story, with quantum fluctuations serving as the opening lines. But how does this connect to the Big Bang? Think of inflation as the moment when the universe took its first breath, expanding faster than the speed of light. During this explosive growth, those tiny quantum ripples were imprinted onto the fabric of space-time, creating slight variations in density. Over billions of years, these variations grew under the pull of gravity, forming the structures we observe today. In a way, the entire cosmos is a result of these microscopic tremors, a cosmic symphony born from chaos. Now, what if we told you that black holes might play a role in this grand cosmic dance? These enigmatic objects, with their immense gravitational pull, could be intricately linked to the way space-time behaves on both the smallest and largest scales. But that's a story for the next chapter, one that takes us even deeper into the mysteries of the universe. What happens to information when it falls into a black hole? This question has puzzled physicists for decades, and it's at the heart of the black hole information paradox. According to quantum mechanics, information can never be destroyed. It's a fundamental rule of the universe. But black holes, with their immense gravitational pull, seem to defy this. Once something crosses the event horizon, it's gone forever, or so we thought. Enter the idea of black hole firewalls. Some physicists propose that instead of a smooth, uneventful journey into a black hole, there's a fiery wall of energy just inside the event horizon. This firewall would destroy anything that enters, effectively erasing information. It's a radical idea, but one that attempts to reconcile the paradox by suggesting that information isn't lost, it's obliterated in a way that aligns with quantum principles. Then there's the concept of soft hair, a term coined by Stephen Hawking and his colleagues. Imagine the surface of a black hole being covered in incredibly fine, low-energy particles, soft hair. These particles could store information about what falls into the black hole, encoding it in a way that's preserved even as the black hole evaporates over time. This theory offers a glimmer of hope that information isn't truly lost but instead transformed and stored in a way we're just beginning to understand. As physicist Leonard Susskind once said, "The universe is not a garbage can, it keeps its receipts." This poetic statement captures the essence of the paradox: information must be preserved, but how? These new theories, from firewalls to soft hair, are reshaping our understanding of black holes and, by extension, space-time itself. Could black holes be the key to unlocking the deeper mysteries of the cosmos? Their ability to warp space-time to such extremes makes them a natural laboratory for exploring the fabric of reality. But what if space-time isn't just influenced by black holes? What if it's also shaped by the existence of other universes? This brings us to the multiverse, a concept that suggests our universe might be just one of many, each with its own unique laws of physics. Could interactions between these universes leave imprints on space-time, creating ripples we've yet to detect? The idea of the multiverse opens up a whole new dimension to the conversation, one that ties together black holes, information, and the very structure of reality. Let's explore that next. What if our universe is just one thread in an infinite cosmic tapestry? The idea of a multiverse, countless universes existing alongside our own, has fascinated scientists and dreamers alike. But here's the twist: in this vast multiverse, space-time itself might not be uniform. Picture a cosmos where every universe has its own unique fabric of space and time, each bending, stretching, and behaving in ways that defy our current understanding of physics. Think about it. In one universe, time might flow backward, while in another, space could be folded into dimensions we can't even fathom. Some universes might have gravity so weak that stars never form, while others could be so densely packed that black holes are as common as planets. The laws of physics as we know them might not apply universally. As physicist Brian Greene once said, the multiverse could be a patchwork quilt of realities, each stitched together with its own set of rules. This raises profound questions about the nature of reality itself. If space-time can vary so drastically across universes, what does that say about the fundamental truths we take for granted? Are the laws of physics simply local bylaws, unique to our corner of existence? And if so, how do we even begin to explore or comprehend the infinite diversity of the multiverse? Now, imagine standing at the edge of this cosmic mosaic, peering into the infinite possibilities. What would it mean if every choice, every event, spawned a new universe with its own space-time structure? The implications are as dizzying as they are awe-inspiring. And as we inch closer to understanding the multiverse, we're also forced to confront the ultimate question: what is the true nature of space-time? Is it a fixed framework, or is it as malleable and varied as the universes it contains? This brings us to the final frontier of our exploration, a theory that seeks to unravel the deepest mysteries of space-time itself, a concept so profound it might just redefine everything we think we know about the cosmos. What if everything we know about space and time is just a fragment of a much larger, more intricate puzzle? As we reach the final stop on our journey through mind-bending space-time theories, we encounter the ultimate question: is there a single framework that can explain the true nature of reality? Enter string theory and loop quantum gravity, two bold attempts to unify the cosmos into one coherent picture. String theory suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings dancing in higher dimensions could explain everything from gravity to quantum mechanics. Imagine the universe as a grand symphony, with each string playing its part in the cosmic orchestra. But here's the catch: string theory requires 10 or even 11 dimensions to work out, dimensions we can't see or measure directly. As physicist Brian Greene once said, the universe is like a cosmic onion with layers upon layers waiting to be peeled back. Yet, despite its elegance, string theory remains untested, leaving us to wonder if it's a glimpse of truth or a beautiful mathematical mirage. On the other hand, loop quantum gravity takes a different approach. It proposes that space-time itself is woven from tiny, discrete loops, like a fabric stitched together at the smallest scales. This theory challenges the smooth, continuous space-time we're used to, suggesting that reality might be pixelated at its core. Carlo Rovelli, a leading proponent of the theory, describes it as a universe where space is not a stage but a dynamic, ever-changing entity. While loop quantum gravity offers tantalizing insights, it too struggles to bridge the gap between quantum mechanics and general relativity, leaving us with more questions than answers. These theories represent humanity's boldest efforts to decode the universe, but they also highlight the immense challenges we face. The deeper we dig, the more elusive the truth seems to become. Could we ever fully understand space-time, or are we destined to keep chasing shadows in the cosmic dark? As we wrap up this exploration of space-time theories, let's take a moment to reflect on how far we've come. From the warping of gravity to the entanglement of particles, each theory has peeled back a layer of the universe's mysteries. Yet, the ultimate nature of reality remains just out of reach, a tantalizing puzzle waiting to be solved. So, as we step back and look at the cosmos, perhaps the most profound question isn't just about space and time, but about our place in this vast, unfolding story. What do you think lies beyond the veil of our current understanding? As we wrap up this journey through 30 mind-bending space-time theories, it's clear that our understanding of the universe is still just scratching the surface. From the bizarre implications of wormholes to the mind-stretching concept of multiverses, each theory offers a glimpse into the profound mysteries that govern existence. Together, they remind us that reality is far stranger and far more beautiful than we often realize. These ideas don't just challenge our perception of space and time, they invite us to rethink what it means to exist in this vast, interconnected cosmos. The collective impact of these theories is nothing short of transformative. They push the boundaries of science, philosophy, and imagination, showing us that the universe is a place of endless wonder. Whether it's the elegance of Einstein's relativity or the speculative thrill of quantum foam, each concept adds a new layer to our cosmic story. And while many of these ideas remain unproven, they inspire us to keep questioning, exploring, and dreaming. As you reflect on these theories, consider this: the universe is not just something to observe, it's something to engage with. Every discovery, every unanswered question is an invitation to dive deeper into the unknown. What do you think about these ideas? Do they spark curiosity, wonder, or even skepticism? Share your thoughts in the comments below. Let's keep the conversation going and explore these mysteries together. Before we go, let's take a moment to marvel at the sheer beauty of the cosmos. As Carl Sagan once said, somewhere, something incredible is waiting to be known. That's the spirit of discovery, the belief that the universe is full of wonders we've yet to uncover. If you're as captivated by these ideas as we are, don't forget to subscribe for more mind-expanding content. The cosmos is vast and there's so much more to explore. See you in the next